who were at the first lecture know, and those of you who weren't will discover that you're in for a treat. The topics have this wonderful apparent simplicity that you can explain the problem to a bright high school student. And then when you hear the way the explanation goes, at least for me, I'm reminded in the best possible sense of the expression of something Serge Lang used to like to say, it's easy when you know how. And now I turn it over to James.
Okay, thanks a lot for the introduction. So I'll just start sharing my screen. So hopefully you can see the title slide.
Yes.
Okay, great. So thanks a lot, everyone, for coming along to this second lecture. So I'd like to talk about digits of primes, but maybe I should mention beforehand that the work that I'm going to talk about today is closely related to and partially inspired by some work of Jean Bourgain, also on digits of primes, which predated my work. And obviously, I'm very sad that normally with the Minerva lectures, I would be able to visit Princeton and I'll be hanging around for a couple of weeks and I'll be able to chat to lots of people about mathematics. And of course, Jean Bourgain was a great, huge figure at Princeton, which made trips and chats like this all the more valuable. So of course, it's exceptionally sad that Jean Bourgain passed away. The other thing that I'd like to say about this topic is that it maybe has a slightly recreational feel to some of the questions that I'm going to talk about today. So I think it's quite fun to think about these questions, even if they are recreational. But maybe I'll start off by giving a little bit of context as to maybe some slightly deeper reasons as to why I think questions like the one I'm going to talk about today are interesting. So actually, the most basic kind of question that I like to spend my time thinking about is you give me some set of integers, let's call it A, and the challenge for me is to try and work out how many primes there are in this set A. So, for example, you could give me the set of integers below some number x, and then I would be asked to say how many primes are there less than or equal to x. So a simple answer to this is given pretty satisfactory by the prime number theorem, but more refined answers to this first example lead you into the territory of the Riemann hypothesis. Another set that you could give me would be the prime shifted along by 2, and then the challenge for me would be saying how many twin primes there are, which of course we don't know at all. And similarly, another set that you might choose could be values of some polynomial, and maybe to make it interesting, you'd want the polynomial to be irreducible and not have all its values the multiple of some fixed number. So you could take a polynomial like the polynomial n squared plus 1, and then the question would be how many primes are there of the form n squared plus 1? And this is another one of these 100-year-old, at least, famous open problems that we don't really know how to answer. And in this level of generality, for a completely arbitrary set of integers, this question is completely hopeless. But if the set of integers that you give me maybe has some nice structure to it, maybe we can hope to say something non-trivial about counting the number of primes in it. Like we can say something non-trivial about this first example. So there's basically two types of structure which we typically use in examples, which typically are the examples where we're able to count primes have. So there's variations on that first example, the number of integers less than or equal to x, which I'm going to call in some nebulous fashion linear structure. And roughly, if your set of integers has some linear structure to it, then there's fairly well-developed techniques from multiplicative number theory and the theory of L functions that can help you try and count the number of primes in this set. So examples here might be the number of integers up to x, or the number of integers up to x in an arithmetic progression mod q, or the number of integers in some short interval. And in each of these cases, the question can be related to the distribution of zeros of L functions, and depending on what sort of knowledge you have, maybe you can answer the question, or you can answer the question conjecturally under some version of, say, a Riemann hypothesis. But then there's also some slightly more general things than just sets with direct linear structure, where there's sets with a certain amount of multiplicative structure when you can use techniques from additive number theory, particularly bilinear sums, which can help deal with these slightly more complicated sets. So for example, you could look at Diaphantine approximation by prime numbers. So this was mentioned in my talk, my first talk last time. Or another question would be Vinogradov's 3 primes theorem. So looking at the primes of the form n minus p1 minus p2, where you're thinking of p1 and p2 being primes, and n is some fixed large odd number. It's slightly strange in some ways calling this multiplicative structure, because you really want to rule out a certain amount of multiplicative structure, but the only way we know how to rule out that multiplicative structure is to use some other a sort of affiliated multiplicative structure. But these are fundamentally the two types of structure that we're able to make use of in the examples where we are able to count primes. And for several of these sets, their density in the set of all integers of the same size is maybe quite small. So for example, if we're looking at arithmetic progressions mod q with integers n up to x, if q is a small power of x, then this is a sparse set. It maybe contains x to the power 0.99 elements less than equal to x. Similarly, if I'm just looking at a short interval, and similarly for this Diaphantine approximation problem, when I'm trying to approximate it and make alpha n modulo 1 very small for some fixed real number alpha. And in general, as the underlying set of integers gets sparser, the question gets more difficult, and you have to work harder to try and prove the existence of primes in these sets. And if it becomes sparse enough, then somehow all the techniques that we have available to us just fail somewhat miserably and they break down. So the current world records for sets with very linear structure is counting primes in short intervals. And so it's a result of Baker, Harman, and Pintz that you can get at least the lower bound of the right order of magnitude for the number of primes in a short interval of length x to the power 0.525. So it's a famous question of Legendre, whether there's always a prime between any two consecutive square numbers. That's roughly equivalent to showing primes in an interval of length x to the power 0.5. And so this is some approximation to that, but we don't know how to answer Legendre's question, even if we assume the Riemann hypothesis. If you look at slightly more complicated sets that don't just have this linear structure, but they have some sort of multiplicative structure, then the sparsest examples are essentially variations on a result of Heath-Brown, which allows you to count primes of the form x cubed plus 2 times y cubed. So there's a fairly recent result of Shannon Lee, who allows you to count primes of the form x cubed plus 2 times y cubed when y is a bit smaller than x. And that would have the world record for the sparsest sets of numbers. And the key multiplicative structure in this example, which allows you to count the primes, which is maybe not obvious at all if you're thinking of it as just x cubed plus 2 times y cubed, is that x cubed plus 2 times y cubed can be related to the norm of ideals or elements in the algebraic number field Q adjoins the cube root of 2. And then the multiplicative properties of the norm allow you to make use of some underlying multiplicative structure. So an extreme example of this is that it was a conjecture of Hardy and Littlewood about the number of primes which can be written as the sum of 3 cubes. They conjectured a precise asymptotic formula, but that asymptotic formula is not known. But the only way we know how to show the existence of primes which are the sum of 3 cubes is basically through Heath-Brown's result, where you take 2 of the cubes to be equal to one another. And here you take a huge gambit, you're losing a huge amount in terms of the density, but what you gain is a certain amount of multiplicative structure, and that's what allows you to count primes in this case. So I want to talk about digits of primes, and in particular today, I'd like to look at the somewhat strange set of numbers that have no decimal digit equal to 7. You can ask the same question in different bases, and you can remove a different number, and everything I say here will work for any digit removed in any base, provided the base is bigger than or equal to 10.
Well, but can you remove like 2 digits, or is that bad?
Okay, so I mentioned before that that these questions about counting primes get much harder as the underlying set gets sparser. So removing more digits makes it sparser, but increasing the base means that it's less sparse. And so you can remove multiple digits if your base is big enough in terms of the number of digits you want to remove.
So it's a cutoff based on, like, you know, if the set is n to the 0.8 or more things up to n, you're happy, or like for some explicit 0.8.
Okay, it's not quite that nice, and so it so you could say something like that if you were maybe removing consecutive digits, but if you want to remove k digits, then your base has to be big enough in terms of k, and it's not quite as nice as just the underlying set has to have density at least x to 0.99 or something like that. Unfortunately, as k tends to infinity, for completely arbitrary sets of digits that you're removing, you would need the density to the exponent to tend towards 1. But you can remove multiple digits, and you can have a result of the type that you are asking for, where there's a single threshold which works for any number of digits in any base if you're just removing maybe consecutive digits, because they're arithmetically simpler.
Maybe a fairer question is, did you work hard to get to 10? Or did that fall immediately into your lap? Because that's obviously where you want to stop.
I had to work really annoyingly hard to get to 10. So it was quite a fun project in the sense that there was a very easy number. Once you had the basic skeleton of the argument, you knew that you should be able to get a result for sufficiently large B. And then there's a question as to, can you get down to a base which is maybe the sort of thing that we care about, like base 10 was my obvious target. And it was quite satisfying in the sense that every time you had a new idea, it would reduce the base down slightly, and these were very compatible with one another. But I was stuck. So originally I proved it for base 1,000,000, then it came down to base 1,000, then 100. It's a sequence of decreasing integers, so it's going to converge, but it wasn't quite clear what it was converging to. And I was stuck at base 13 for quite a long period of time, which was very frustrating indeed. But fortunately, I managed to limp over the line and just about get down to base 10. So, okay, maybe I've been preempted slightly, but the question that I'd like to think about, therefore, is if I'm taking this set where I'm looking at numbers with no 7 in their decimal expansion anywhere, how many primes are there in this set A? So just to recap a few things, numbers with no 7 in their decimal expansion are a sparse set. They contain about x to the 0.95 integers less than or equal to x. And so the vast majority of numbers always have a 7 in their decimal expansion. And so we're trying to find a very rare property. It's much rarer to not have any 7s in your decimal expansion than it is to be a prime number, for example. And moreover, this set A doesn't have any terribly obvious linear structure or multiplicative structure in the senses that I mentioned before. There's not any natural multiplicativity or terribly linear structure in this set, but it will have some exceptionally nice Fourier properties, which is really what we're going to be able to exploit. And it's the fact that this set maybe doesn't match up so nicely with typical approaches, but has some other unusual structure which one is able to exploit for this problem, which is maybe what I find most interesting in the abstract sense. But either way, I want to count the number of primes which have no 7s in their decimal expansion. I feel that this is a natural enough question, even if it has a fairly recreational feel to it. But before we get into thinking about any of the details, maybe we should guess how many primes would there be, maybe with k digits, that have no 7s in their decimal expansion. So the most naive thing you could say is that primes of size x occur with density around 1 over log x. So you might expect the number of primes in a set of integers a to be roughly the number of primes of size x should be the number of integers in a of size x divided by log x. And this would indicate that the primes are somehow, the property of being prime is just independent from the property of being in your set. But unfortunately, it's clearly not the case that being prime is completely independent of properties of the digits. So the last digit of a prime is obviously quite heavily restricted to being either 1, 3, 7, or 9 in base 10, at least for primes bigger than 10. Also, of course, there's other properties like the sum of the digits of a prime number can't be a multiple of 3 for primes which are more than 1 digit. But the sum of digits property doesn't seem to be so directly related to the property of having a 7 or not having a 7. But a natural thing to do if you want to think about a question like this is to try and think about the ways in which the property of being prime can be related to its decimal digits. And maybe you sit around and you think about this for a little while and you decide that clearly there's this property about the last digit being 1, 3, 7, or 9 is related to its decimal digits and related to the property of having 7s or not 7s in the decimal expansion. But maybe that's the only easy one that we can come up with. And so let's pretend that that's the only relevant property. And let's see if we can guess the number of primes with this property. So what I want to imagine is I'm going to choose a random integer with k digits in base 10, such that it ends in 1, 3, or 9. So I can calculate the probability that a random such integer lies in A. We've fixed the final digit to not be a 7, and then I just need to make sure that the first k-1 digits all avoid a 7. So there's 9 choices for each of those k-1 digits. And so the probability that such a random integer lies in my set A of having no 7s in the decimal expansion is just 9 to the power k-1 divided by 10 to the power k-1. Similarly, I can calculate the probability that n is prime, and this is just counting primes in arithmetic progressions mod 10. And asymptotically, this is 5 divided by 2 times log of the size of the numbers that we're looking at, just by Dirichlet's theorem on primes in arithmetic progressions. And so if I thought that the only relevant property of connecting being prime and having no sevens in your decimal expansion was the final digit, then once I've conditioned on having the final digit 1 through or 9, these two properties of being in A or being prime should be independent of one another. And so the probability that you're both prime and in A should look like the product of the two probabilities. And so I would guess that the probability that n is a prime in A would just be n to the power k minus 1 divided by 10 to the power k minus 1 times 5/2 times log of 10 to the power k. So therefore, I might guess the total number of primes would be this product of the two probabilities times the number of choices of n, which is 3 times 10 to the power k minus 1, which would actually give you 5/6 of the naive choice if you were just saying that primes occurred with probability 1 over log x. Obviously, you could do the same calculation, and if you were excluding a number that wasn't 1, 3, 7, or 9, you would get a different answer coming out here, which would be slightly bigger than the naive choice, because you're somehow biasing to make it slightly more likely to be a prime if you're excluding the last digit 2, for example. So this is maybe a fairly natural conjectural guess that you might guess the probability that a number in A of size x is a prime is about 1 divided by log x times 5/6. And the main result that I'd like to talk about today doesn't quite prove this, but it gets pretty close. So in particular, it shows that A contains infinitely many primes. And if you want to count the number of primes of size x, which have no sevens in their decimal expansion, you get upper bounds and lower bounds of the correct order of magnitude. But I can't get a precise asymptotic formula, so I'm off by maybe a factor of 100 or something compared to what you might expect. So I guess one thing to note is that you can't expect a completely neat asymptotic formula in the sense of some counting function being some constant times the size of A divided by log x, well, x to the power 1 minus c divided by log x, since the number of integers with no 7 in their decimal expansion oscillates depending on what scale you're looking at. The number of integers less than 7 times 10 to the k with no 7s in their decimal expansion is the same as the number of integers less than 8 times 10 to the k with no 7s in their decimal expansion, because all the middle ones begin with a 7. But nonetheless, even though I'm not able to prove it, I would conjecture that the naive guess that we put out, once you take into account this oscillatory factor, is correct, and you should be able to get an asymptotic formula, which is 5/6 divided by log x times the number of elements in A.
A question about this 100 factor. So is this some pretentious, like this proof doesn't use any complex analysis or anything, right? And so I know that for PNT, like if you use only elementary methods, it's somehow easier to get this 100 than to get the 1. So is there some is there some connection there? Like what's, is this like generalizing some parts of the proof of PNT, some elementary part, like, okay.
Okay, so getting upper bounds, which are off by a constant factor, you can normally do using sort of elementary sieve methods, and this works in huge generality. So this upper bound here is actually pretty straightforward to prove once you get into things, and it's not really the main content of the result. However, in general, lower bounds are much, much harder to prove, and they tend to require all the same sorts of ingredients that go into these technical proofs of getting asymptotic formulas for primes, but there is often a set of techniques that say if you have some arithmetic information about your set that's relevant for counting primes, but it's not quite strong enough to get an asymptotic formula for primes, you can nonetheless get a lower bound of the correct order of magnitude. So you should think of the upper bound as being much weaker, but the lower bound is really not being a trivial thing at all. And it's not just, it's using exactly the same techniques that would be getting you an asymptotic formula. It's just that in the hard analysis setup, certain numerical restrictions mean that you aren't quite in the range when you get an asymptotic formula. Does that make sense?
Yeah. So removing the 100 is still hard though, or like from the upper bound.
Yeah, okay. So I mentioned before that there's this, the question gets harder as this underlying set gets sparser, and correspondingly it gets easier as the underlying set gets less sparse. So if you look at a bigger base, then I can get an asymptotic formula of precisely the type that I have at the bottom here. So if you want to look at primes in base 100 where you remove one digit, then I think then I should be able to get an asymptotic formula for that. So it is difficult. It's a kind of technical limitation of the methods, but the methods that I'm using are, this is maybe sort of 50% of the way to an asymptotic formula, as opposed to something much, much weaker than an asymptotic formula. Does that satisfy the question, or?
Yeah, sure.
Okay.
Thanks.
So may I ask a question? Maybe it doesn't make sense, but so not all digits are the same, right? Like if you had this guess with, let's look at the last digit, what can it be? When you remove 7, you remove some potential primes, right? If you would remove 2, so not all digits should be the same, right?
Yeah, so there's this constant factor 5/6, which has, and this is sort of less than 1 because 7 is co-prime to 10, and you get 5/6 if you're removing the digit 1, 3, 7, or 9. However, you will get a different constant that's bigger than 1. It'll be whatever it is to make the average, make the constants average to 1, but this 5/6 would be a different constant which is slightly bigger than 1 if you were removing a digit which has a common factor with 10. So if you're removing 0, 2, 4, 6, 8, or 5.
But it still,
sorry, go ahead.
But it still will be like what you would guess from the previous analysis.
Yeah, so the previous analysis guess would work for any base bigger than 2, and yeah, it would naturally give you a different constant, but it will give you the same results.
Thank you.
Okay, are there any other questions about the statement of the result? So the key point is that there are infinitely many primes with no 7s in their decimal expansion, and in fact you can count them up to size x with the loss of maybe a constant factor. Okay, I will move on then, and I'd like to talk about some of the ideas that go into the proof to give a high-level overview of the flavor of different arguments that come up. So fundamentally, the argument is Fourier analysis. So in analytic number theory, we would call this the Hardy-Littlewood circle method, but that's maybe if you haven't seen this before, that's maybe just a somewhat grand name for a Fourier inversion formula. And all this says is that if I want to count primes in essentially an arbitrary set A up to x, I can rewrite this using Fourier inversion as some correlation sum between the Fourier transform of the primes and the Fourier transform of the underlying set. And the nice thing about this is that it allows me to study these two functions separately from one another. So I can just try and get a very good understanding of the Fourier transform of the primes, and I can try and get a very good understanding of the Fourier transform of whatever set of integers that it is that I'm looking at. So today we're interested in the set A of numbers with no 7s in their decimal expansion. So we'll want to look at the Fourier transform of numbers with no 7s in their decimal expansion. And so by the Fourier transform of this set, I'm just saying the Fourier transform on the unit torus. So at theta in the unit torus, for theta between 0 and 1 is just the sum of e to the 2 pi I a times theta for every element A in my set. And the philosophy of the Hardy-Littlewood circle method is that there should be a very small number of these Fourier frequencies for which the Fourier transforms take very large values, and then for the vast majority of the other Fourier frequencies, both the Fourier transforms should be very small, and hopefully they should therefore just give a negligible contribution. So if you can understand these few key Fourier frequencies, then this allows you to get a main term approximation to the quantity you want to consider. Now, if you're used to this, you might be slightly surprised that I'm saying this, because this sort of setup of looking at linear equations, in my case, I was looking at the linear equation p minus a equals 0, where a is a number with no 7s in its decimal expansion and p is a prime. This sort of setup is known to work pretty well for equations with 3 or more variables, but to work very poorly for linear equations in 2 variables. So for example, I mentioned before that we can solve Vinogradov's 3' theorem. If n is a large odd number, then this Hardy-Littlewood circle method works very well for showing that you can count the number of representations of n as the sum of 3' numbers, and in particular show that there is a representation of n as the sum of 3' numbers. But if you try and do exactly the same argument to attack Goldbach's conjecture and try and write an even number n as the sum of 2' numbers, then this whole method seems to completely break down, because the philosophy was there should just be a small number of Fourier frequencies which are giving the main contribution to the overall integral, and everywhere else the Fourier transforms should be small. But it turns out that they're not small enough in 2 variable equations for you to possibly be able to just trivially discard them. And so this is a well-known obstacle to, say, trying to prove Goldbach's conjecture or the twin prime conjecture using this sort of somewhat simple Fourier analysis type argument. So it's therefore maybe surprising that I do have a binary equation just using 2 variables where I'm going to claim to use the Hardy-Littlewood circle method. And the reason that the circle method works here, whereas the normal heuristic arguments would say it shouldn't possibly work, is that there's some unusual Fourier structure in this set of numbers with no 7s in their decimal expansions, which means that the Fourier transform actually behaves much nicer than maybe a random Fourier transform. And it's this extra Fourier structure that means that the normal heuristics don't actually apply in this context, and you can just about make the method work in this situation. So it's a very, very specific to this set A of numbers with digital restrictions. But let's go back and just think about, we have some expression for the number of primes with no 7s in their decimal expansion in terms of the Fourier transform. And in the spirit of the Hardy-Littlewood circle method, we feel that there should just be a few very structured frequencies when the Fourier transforms of these sets of the primes and sets of numbers with no 7s in their decimal expansion should be large. And because the Fourier transform just completely re-encodes the objects, it's natural that the Fourier transform of the primes should be large at points theta with some sort of arithmetical significance, and the Fourier transform of set of numbers with these digital restrictions should be large at points theta with some sort of digital properties. And indeed, this is the case, that you can think about these heuristically, and you can decide that it should be the case that the Fourier transform of the primes should only be large when you're evaluating at a point close to a rational with small denominator. And similarly, the Fourier transform of numbers with no sevens in their decimal expansion should be large only if you're evaluating it at a point theta, where, so theta is a number between 0 and 1, and we can think about writing it out as a decimal expansion. So it'll be 0 point something, 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 something. And this Fourier transform should only be large if there's very long strings of consecutive zeros or very long strings of consecutive nines in its decimal expansion. And so the Hardy-Littlewood circle method would say that you should only get a main term contribution when both of the two Fourier transforms are simultaneously large. So then there's the question, when can you have a real number between 0 and 1, which is simultaneously close to a rational with small denominator, and it has long strings of zeros or nines in its decimal expansion? And it's not too hard to see that these two things coincide only when your point theta is close to a rational with small denominator, where that denominator itself is a small power of 10. And you can therefore look at these structured points, and you can understand the Fourier transform on these structured points where you're close to rationals with small denominator, or close to rationals with small denominator, which is a power of 10, by understanding the underlying set in arithmetic progressions. So this is a not too complicated arithmetic counting problem. And it turns out that at least if you just concentrate on points theta, which are close to a rational with small denominator, you can get an asymptotic formula for this contribution. This asymptotic formula is precisely the asymptotic that we came up with our naive guess of 5/6 of the size of A divided by the logarithm of the numbers that we were looking at. And the full contribution here is essentially coming from rationals with small denominators that are a small power of 10. So this is fitting perfectly with both our heuristic guess and our philosophy of the Hardy-Littlewood circle method, that there should be a few structured points. And so then what we would be left to do is to show that for all the remaining Fourier frequencies theta, which are not close to a rational with small denominator, there's a negligible contribution from these, and they would only contribute smaller terms. And then we would have a full asymptotic formula for the number of primes with no sevens in their decimal expansion. So if you want to make further progress, you need to start trying to understand these Fourier transforms of the sets. And the key Fourier structure of the set of numbers with no sevens in their decimal expansion is it has a very nice explicit product structure. So the Fourier transform can just, if you're looking at numbers, if your original question was about numbers primes maybe with k digits, then you can basically write your Fourier transform as the product of k different terms, where the kth term is just some very explicit function involving e to the 2 pi I theta, which is some nice continuous function that you can just write down. And moreover, the ith term in the product is just a function of 10 to the I minus 1 times theta modulo 1, and it's continuous. So it has this really nice, very structured property, and this is exceptionally useful for doing analysis. So I said before that we might guess that the size of the Fourier transform should be very closely related to the decimal expansion of the point, the Fourier frequency that you're evaluating the Fourier transform at. So you can think of the value of theta as having a decimal expansion t1, t2, t3, t4, t5, and so on. And then because this function in parentheses just depends on 10 to the I minus 1 times theta and is continuous, the ith term depends only on ti, ti plus 1, ti plus 2, and so on. So ti and then the subsequent digits. But moreover, it mainly depends on ti, and then it depends to a lesser extent on ti plus 1, and then a lesser extent still on ti plus 2, and so on, because it's a continuous function. So to a reasonable approximation, you could approximate it with a function that just depends on ti and ti plus 1. And so therefore, there's some explicit function g, and you can approximate the value of the Fourier transform at theta as this product where you're evaluating this function g at ti and ti plus 1, at 2 consecutive digits. So the first term just depends on the first and second digit, the second term depends on the second and third digit, and so on. And the really nice thing about this is you can now reinterpret this whole size of Fourier transform as a Markov process. So you can think about taking a walk on digits. And if you're standing at time I on digit ti, then you want your transition probability to go into the digit ti plus 1 to be proportional to this function g evaluated at ti and ti plus 1. So this defines a Markov process where you're randomly walking on the digits, and then the probability that you trace out a given particular path will be precisely proportional to the size of your Fourier transform evaluated at the point whose decimal expansion is precisely given by the path that you walk along the digits of. So if you wanted to evaluate the Fourier transform at pi, this would be proportional with a constant of proportionality to the probability that your random walk takes you first starting at 3, then you walk to 1, then you walk to 4, then you walk to 1, then you walk to 5, then you walk to 9, and you're spelling out the digits of pi. And in particular, recasting this as this sort of ergodic problem with random walks means that you can understand everything about this Markov process just by understanding the finite transition matrix. So this Markov process where I'm just defining these transition probabilities, the whole transition matrix is just an explicit 10 by 10 matrix that you can write down. And by understanding the eigenvalues of this transition matrix, you can understand basically the complete distribution of this Fourier transform. So you can understand all moments by just looking at this transition matrix. There's maybe a slight concern that I took this approximation where I'm just looking at 2 consecutive digits, but you can correspondingly take better approximations because fundamentally I'm looking at some infinite dimensional operator, but I'm approximating it by a sequence of finite dimensional operators. And for each of these finite dimensional operators, I can understand all their behavior and all their distribution just through eigenvalues of some finite transition matrix. And in practical terms, this means that any statistical question you might have about this Fourier transform of numbers with no 7s in their decimal expansion, you can understand very well. You can understand essentially any given moment of this Fourier transform and get very precise estimates for it by recasting it as this Markov process. And you can, it's a short explicit numerical calculation to evaluate any given explicit moment, for example. So you can really write these things down. So that means we've got a pretty good understanding of the Fourier transform of numbers with no sevens in their decimal expansion. So the natural thing to do is to then try and get a good understanding for the Fourier transform of the primes. But unfortunately, it turns out that we're not very good at understanding the Fourier transform of the primes. Even under the generalized Riemann hypothesis, you can't prove a bound better than the Fourier transform of the primes is typically of size x to the 3/4, and this would be way too weak for the sorts of bounds that I would need for using the Hardy-Littlewood circle method. So we have to do something slightly different, and basically the only real strong bounds that are maybe sharp for primes is that we can quite trivially estimate the second moment of the primes, which at least shows that most of the time the Fourier transform of the primes is of size about x to 1/2. So this shows that there's a lot of cancellation, at least for typical Fourier frequencies. So because you have some weak statistical understanding of the Fourier transform of the primes on its own, and some strong statistical understanding of the Fourier transform of numbers with no sevens in their decimal expansion, you get some pretty decent joint distribution understanding just from having looked at each one on their own. And the conclusion of all of this is what I call the generic minor arcs that says for the vast majority of Fourier frequencies, this product of the two Fourier transforms which we're interested in is going to be small. So there's some exceptional set, which I'm calling E, which might have a large contribution, but I know that this exceptional set has to be pretty small. And it turns out the numerical bounds on this set are very important for whether this argument will work or not. And so it turns out that it's very important that this exceptional set can be made of size x to the power 0.58 or smaller. So this means that it's fitting with the Hardy-Littlewood philosophy that there should be a small number of structured frequencies which give a main term, and then there should be just other generic noise which just contributes to an error term. This is saying the vast majority of frequencies contribute to an error term, but we still have to understand the possible contributions from this strange exceptional set E, which at the moment we have little handle on. And to do this, we'll need to do something a little bit more sophisticated than just looking at the two Fourier transforms individually from one another. We'll have to try and say something a bit more specific about their joint distribution. So to do this, you need to go a little bit back more to techniques in prime number theory, and it's a basic principle of Vinogradov that you can estimate various exponential sums and quantities related to primes, provided you're good at estimating two auxiliary quantities. So one is related sums where instead of looking at it being over primes, you're looking at it over arithmetic progressions. And the second type of sum is certain auxiliary bilinear sums. And in practice, it turns out that it's these bilinear sums that are always the most complicated things to estimate, and that's normally where we struggle to get good results. And that's very much the case here, that somehow the sums over arithmetic progressions require a small amount of work, but they're not too bad to look at. And it's the bilinear sums which you need to study rather more carefully if you want to understand the contribution from this bad exceptional set of Fourier frequencies. So it turns out that you can write down these complicated looking bilinear sums, and these bilinear sums are sort of sums which depend on two different Fourier frequencies, call them A1 and A2 in this exceptional set. And so you get a different bilinear sum for each pair of Fourier frequencies. And if somehow the two Fourier frequencies looked Diaphantinely generic in some sense, then it turns out you can estimate these bilinear sums in a moderately straightforward fashion, and there's no big surprises, and it works out in the way that you might hope. But there were problems if there's certain Diaphantine problems with these pairs of Fourier frequencies in this exceptional set, which cause these bilinear sums to be much more complicated to estimate. So for each pair of Fourier frequencies, we get some bilinear sum, and we want to understand them, these potential bad pairs, when they cause Diaphantine problems. So with a little bit of work, you can recast these messy looking bilinear sums and these Diaphantine problems as a much more geometric situation, which you can then try and look at through the geometry of numbers. So here's a picture trying to demonstrate this. For every pair of Fourier frequencies A1 and A2, there's this associated bilinear sum, and this bilinear sum is large only if you have a large number of integer lattice points in a certain cuboid in three-dimensional space. So there's some cuboid that just depends on A1 and A2, and you're in a good situation if unless there's lots and lots of lattice points in this cuboid. So you would generically expect the number of lattice points in the cuboid to be roughly the volume of the cuboid, but it's certainly not always going to be the case that you could have a cuboid that lines up with the xy axis and looks very thin and flat. It's very close to the z equals 0 plane, and then you might have many more integer lattice points than the volume of the region. And similarly, you could have your cuboid looking like a very long, thin cylinder that maybe lines up with the z equals 0 and y equals 0 x-axis. And then again, you could have a huge number of points just along the x-axis, but the cuboid could have a very small volume. So what you want to understand is when can a cuboid have too many points, and if you have one of these exceptional cuboids, what does that say about the frequencies A1 and A2 that determine this cuboid? And it turns out that a different way of saying this is there are problems whenever there's many short vectors in Z cubed, which is orthogonal to the vector A1, A2, X. So it's well known that you can get pretty precise answers to this using the geometry of numbers, and you can go back and classify precisely when these obstructions occur. And you only have problems in one of two possible cases. Either your pair of Fourier frequencies lie on the projection of some low height line, which means that there exists some small integers v1, v2, v3, v4, such that this linear equation is satisfied, or your pair A1, A2 lies on the projection of some low height lattice lambda. And in arithmetic terms, this means that the Fourier frequencies A1 and A2 have some simultaneous Diaphantine approximation. So the key point here is that we started out with some completely messy bilinear sums. We managed to handle the bilinear sums unless there was this sort of geometric Diaphantine problem. And then we were able to recast this geometric Diaphantine obstruction as some much more, as one of two fairly rigid algebraic conditions. And we can now separately, we now have suitably rigid conditions that we can understand each of these two cases very specifically and separately from one another. So you can now consider pairs of these bad Fourier frequencies that lie on the projection of a low height line, and you can show you that actually there has to be only a very small number of pairs of Fourier frequencies which lie on such a low height line. And there has to be so few that it turns out the contribution from these potential bad points is negligible overall. And here, to say that there's a suitably small contribution from these pairs of frequencies looking at coming from a projection of a low height line, all we use is the fact that we know that the two frequencies A1 and A2 are restricted to some small set E. So we have absolutely no understanding about the structure of the set E, but just knowing that the set E itself is pretty small means that there can't be many pairs A1 and A2 in this set E for which there's lots of solutions to this linear equation. So this depends quite heavily on the precise numerics of things involved. If A1 and A2 were small numbers, then you can quite easily come up with, so if the VIs were the same size as the A's, then you can obviously come up with a solution to this equation. But it turns out that the VIs are suitably small in terms of the set E, that just by virtue of this being a sparse set, without needing to know anything about the structure, you're saying that there's very few solutions to equations of this type. So that on its own, without using any further structure, happily controls the contribution from lines. But then you also need to control the contribution from lattices. And I mentioned before that this contribution from lattices is when the Fourier frequencies have a simultaneous Diaphantine approximation. So unfortunately, you can't get anything, you can't make any mileage of the fact that the Fourier frequencies are restricted to a sparse set in this case. And so we don't use that at all. But here, instead, we go back and feed this into our original problem and use the fact that if you're looking at this Fourier transform of numbers with no sevens in their decimal expansion on points lying in a lattice, so points with a simultaneous Diaphantine approximation, then the Fourier transform actually can't be concentrated on these points. That you can't have lots of points in a lattice where all their decimal expansions have lots of long strings of zeros or nines in them, unless you're in a very special exceptional lattice. So once we've got this rigid algebraic characterization of what the possible exceptions are, you can then feed that back into the original problem and say, well, if the exception did look like this, then actually the Fourier transform of numbers with no sevens in their decimal expansion has to look pretty small on such sets, and so these don't cause a problem either. So we classified the obstruction, and then we showed that that obstruction actually can't obstruct the thing that we're interested in. So here it's very crucial that we are lying away from the major arcs, because we know that points when you have simultaneous Diaphantine approximations close to a rational with small denominator, where that denominator is a small power of 10, actually contribute a main term. And so here the vital ingredient that we're using is that digital restrictions don't correlate at all with lattice restrictions, and we're outside the major arcs. But if we put all of this together, we can control the bilinear sums, at least in a certain range, by having this lattice and line classification. Now, unfortunately, this range is quantitatively just a little bit too small to use Vinogradov's method to actually count primes, which means that the whole argument that I've just sketched out fails at this point. But fortunately, there's a whole set of techniques in sieve methods which allow a substitute for Vinogradov's principle if you just have some weaker bilinear information. And so then you can rerun the whole argument just using a sieve minorant. And it turns out that this range is quantitatively just good enough for you to get a positive lower bound for counting primes when you're, instead of counting primes with weight 1, you count them with you count integers with a sieve minorant, so you count primes with weight 1, but non-primes with some potentially negative weight. So I basically reached the end of my talk and the end of my time. Here's just a schematic overview again of the different steps that we were using to try and answer this fairly basic question about primes with missing digits. That we wanted to use Fourier analysis to study the whole problem. So this was called the circle method. And the philosophy of the circle method is that there should be a few major arc frequencies that give the main contribution. And this just relied on us understanding primes and numbers with no sevens in the decimal expansion in arithmetic progressions. For the vast majority of Fourier frequencies, we expect the Fourier transforms to be small. And the key thing here was to understand the individual Fourier distributions and this Markov approximation, reinterpreting the size of the Fourier transform as the probability of a certain random walk allowed you to get a very good control over the size of the Fourier transform. However, this left certain exceptional minor arcs where you had to work much harder to understand the joint distribution of primes and numbers with no sevens in their decimal expansion. And the key for this was to understanding certain bilinear sums. The bilinear sums could only be bad if there were problems of a Diaphantine nature, and using the geometry of numbers, you could classify what these potential problems look like as either coming from lines or from lattices. In the lines, we use the fact that we knew that the exceptional minor arcs were small to say that there can't be many points, and so the lines can't cause too many problems. Whereas in the lattices, we use the fact that the Fourier transform of numbers with no sevens in their decimal expansion can't be concentrated on any lattice. And so this potential obstruction actually doesn't cause an obstruction to the bilinear sums that we're interested in. We then had to work with a sieve minorant because we weren't so successful at estimating the bilinear sums. And it's because we estimate using a sieve minorant that we're only able to get upper bounds and lower bounds of the right order of magnitude. If we were able to estimate the bilinear sums in a slightly wider range, then you would be able to get the asymptotic formula that I conjectured at the beginning. So hopefully that's a fun blend of different ideas, answering a question which is deceptively simple to state, but also has some interest in the sense that this is answering a binary question using a set that has a certain amount of Fourier structure, but no explicit linear or multiplicative structure in the same way. So thanks a lot for listening. I hope you enjoyed the talk.
Thank you. Okay, so the floor is open to questions.
Okay, let me ask two quick questions. Excuse me. Firstly, you mentioned Bergin at the beginning, so he proved something about the Fourier transform of this characteristic function. I assume that you're alluding to some work of his or not?
Yeah, so it's actually slightly embarrassing that Bergin wrote 2 papers about pre-assigning the binary digits of primes. And when I did this work, originally I was aware of the first paper, but I hadn't actually realized that he'd written the second paper. So there were several ideas that I came up with that I was quite proud of. And then when I realized he had this paper, I had a look at it and I realized that Bergin had got there before me for some things. But yeah, he, I guess he didn't, he wasn't gunning for, he was happy to work in a much denser situation. So he was pre-assigning a positive proportion with an unspecified constant of the digits of primes in base 2. And yeah, correspondingly, he needed some estimate for the distribution of this Fourier transform. I think he only needed a L1 bound. For the
so that's what I had in mind, that he made an L1 estimate, yeah, for the Fourier transform. But the second question I have is related to that. Basically, this is the map X goes to 10 times X on the interval, and you're looking at its itinerary and saying, I'm omitting a digit. You could look at other dynamical systems and omit a digit, and probably, as long as you have a similar structure, get into your ballpark, not maybe 10, but just some. Have you thought of such problems?
Okay, yeah, I haven't thought about such problems, but I agree that there's that yeah, you should be able to say, so you could, for example, say.
So your
I just
dynamical
want-
system could be somewhere else even.
yeah, there's a whole zoo of questions that you could ask about this. I guess I haven't really given too much thought about it. You can certainly exclude different digits in each place, for example. And yeah, I would have thought that you should have the same sort of, provided you have this sort of Fourier product structure, which you should do for lots of the sorts of maps that you're talking about, provided you're just looking at linear things at each stage. Then yeah, I'm sure the quantitative estimates completely go out the window, but just qualitatively, provided you have this product formula, I would have thought you should be able to do something similar along the same lines. At least I'll be optimistic about it.
Thanks.
I should mention, I guess, yeah, for the Bourgain L1 bound, I guess this was really, the L1 bound was this work of Maudry and Rivat on sums of digits of primes.
Right. So they certainly think dynamically. Yeah. Yeah. But I assume that's where you started with seeing that kind of feature that opened the door for a binary problem. As you said, that's what's unusual. Yeah.
Yeah, it's the fact that you have an L1 bound that's better than what a random Fourier transform would be. That's really what's opening the door here.
Yeah. Thanks. Yeah.
What happens, suppose you want to know something about the representation in two different bases. So suppose I want to know about primes that miss a digit in base B1 and miss some other digit in base B2. Can you say something about this?
Okay, I did think about this. Some related questions to this briefly, and you would hope that the same basic structure of the argument works, but there's potential problems if, so you need to understand these potential Fourier frequencies that have long strings of zeros in one base and long strings of zeros simultaneously in a different base. And I don't know how to say that, so it should be the case that such Fourier frequencies are rare. It should be difficult for a real number to have very long strings of zeros in base 2 and very long strings of zeros in base 3. But I don't know how to show this. You can say some things using sort of linear forms and logs in really extreme versions, but it's when, but numbers where maybe 99% of their digits are 0 in base 2 and 0 in base 3, but 1% of their digits can be anything. I have no idea of how to control the number of such points, really. So that's where, so I think my method in principle should be able to answer these questions, but I don't know how to rule out the possibility that there's lots of real numbers that have long strings of zeros in base 2 and simultaneously long strings of zeros in base 3. If you could do that, then I think optimistically things should work out fine. But I think that's the kind of key obstruction.
I see. So you're saying that the main thing is to understand just the behavior of numbers in two different bases, and then asking them to be primes would sort of work out well.
Yeah. Yeah, that's only one way of phrasing it, that I kind of can't make this method work, and I don't have good enough estimates just on integers in two different bases simultaneously. And if you could get suitable estimates just for integers, then this method should allow you to also prove it about primes, provided it's quantitative in the same way. Yeah.
Okay, thanks.
I think the question about two different bases simultaneously is related to some questions in computer science as well, because I think a couple of other people have asked me about this. I don't have a reference for what the problems are in computer science, but I think there's some hash functions or something that are related to whether certain numbers have certain properties simultaneously in two different bases. And these are still open.
James?
Hi, Henrik.
Yes. Are your results effective?
Yes. So, okay, naively, I'm using the Ziegler-Walfisz theorem to understand primes in arithmetic progressions, but I only really need the Ziegler-Walfisz theorem for when the modulus of the progression is a power of 10. And so because this is a powerful modulus...
It's just logarithm, yeah, not log square. Up to log square, you have effective. Using Goldfeld, you can go even a little bit further effective.
Yeah, so I need to go further than log squared. So I need to go up to an arbitrary power of a logarithm, but I only need it for powerful moduli.
Powerful modulus, and that's all effective. Yeah, right.
Yeah, so it's effective, but it's because
of Gallagher and others, right?
Yeah, exactly.
Yeah.
So yeah, it can be made. So naively, it's not effective, but yes, it can be made completely effective. But it needs to, use these results on kind of Gallagher type on smooth moduli to get a better zero-free region because you have good character sum bounds.
I guess you didn't compute the constants.
I did not compute the constant.
Since you are still alive.
What information do you use about primes in the proof?
Okay, so I use the fact that the primes have this type 1, type 2 decomposition, crucially, and I use the fact that I can understand primes in arithmetic progressions to small moduli pretty well. And other than that, I hardly use anything about the primes. But I am using the full sort of type 1, type 2 machinery, which is basically almost the only, I guess, I'm using all the type 1, type 2 style machinery, which is normally all we know how to say anything about the primes anyway. So I'm very much using kind of type 1, type 2 sums, but yeah, it's limited to being able to estimate type 1, type 2 sums and then primes in arithmetic progressions.
So basically any decent arithmetic sequence, you should be able to get the same result.
Yeah, anything that satisfies a version of Vaughan's identity or something, I would have thought that you should be able to get the same result.
Thanks.
You were working in base a trillion,
Yeah.
would you use the Maynard idea?
Sorry, I didn't quite hear that question. Could you repeat?
If you were working in base 1 trillion, would you have needed to use a sieve Maynard?
Okay, I don't know if it's my audio, but it came out as muffled. I don't know if someone else could heard if they could repeat the question.
I think the question was whether you would need to use the sieve minor int if you were willing to use a much larger base like 1 trillion.
Oh, okay, yeah, that's a great question. Sorry, I couldn't hear you. It came out really muffled on my end. And yeah, you're right that you don't need to use the sieve minor int if you have a large enough base. So the question gets easier as the base gets bigger because the underlying set is less sparse, and this correspondingly means that this range of bilinear sums, which I'm able to handle, gets bigger as the underlying set gets less sparse, and at some point it gets big enough that I don't need to worry about sieve minor, and when I don't need to worry about sieve minor ints, I can get a full asymptotic formula. So I don't know exactly what base that would kick in at, but it might be for base 20 or base 100 or something like that. that you can get an asymptotic formula because you don't need to use the sieve minorant, and you can estimate the bilinear sums in suitable ranges. So maybe if you're counting primes with your toes as well as your hands, you can get by.
I don't know, do you hear me?
Yeah, I can hear you.
I was very pleased to learn that geometry of numbers comes in helpful. And I have a probably unfair question. Suppose you only have prime numbers where the digit 7 occurs with a smaller frequency. This is a very vague question, of course. Can you handle that?
Yeah, I feel that. Yeah, I feel that you should be able to. You should be able to specify that the digit 7, occurs 10 times or occurs a kind of like asymptotic positive proportion of the digit. So you could say that I want primes where I don't care about any of the other digits, but the digit 7 occurs precise, like between 0.99 and 1.01% of the digits. And I feel that these methods should work for that as well. Okay, I need to check a few things.
Is that Wolfgang? Is that
yes,
Wolfgang?
yes, that's my name. Yes.
Fantastic to see you. That's Wolfgang Schmidt asking you that question. And the minute geometry of numbers comes in, I'm sure he asked you a question.
Yeah, well, I'm very impressed by your work.
Oh, thank you very much.
This has maybe nothing to do with the math, but why, just out of curiosity, why did you pick 7 as sort of the example?
Okay, that's a good question. I feel like I've done okay with all the other questions, and I'm going to flounder more with this question. I guess I want to choose a number that doesn't seem like I'm fixing things in some way, that the same method basically works for all digits in more or less the same way. It turns out that, kind of interestingly, some digits are arithmetically slightly easier than others. So it's slightly easier to find primes without the digit 0 than it is to find primes without the digit 5, due to the kind of likelihood of carries occurring. I was trying to choose 7 as a random looking number between 0 and 9 that wasn't having any special properties. And I thought people might feel that I was cheating and it was somehow special to do with the digit if I chose 0 or 5 or 2 or something.
Apparently, if you ask people to come with a random number, they often pick 7 because
yeah. So I was going to say this as well, that 7 apparently is a very popular choice for a random number.
Like if you ask people to
make it less random or more random, but
like if you ask people to generate a string of random numbers, it will have a lot of 7s. It will have a lot of it'll have more odd numbers and more numbers that are larger than 5. You ask for like a random bunch of random digits because like 7 is somehow more random than 2. It's some psychological thing.
Yeah, so it was this sort of psychology, and I'm not sure how much it was me falling for the psychology or me using the psychology, but some combination of all of the above.
I thought that you have chosen 7 to be sure that your set A does not contain 57.
Grothendieck's prime, is this right?
Yep. Fake prime.
You mentioned that the counting function is oscillatory, and that is a bit of a pain. But for example, example, in study of the first digit phenomenon, you can get rid of the oscillations by weighting an integer n by 1 over n, and then essentially taking relative density. So do you think that that looking at that might make some things a little easier, because the oscillations are always annoying?
I guess okay, you need to be slightly careful about weighting with 1 over n, because you don't want things to converge. Yeah, I would have thought that there's a few cheap tricks that can this is a slight technical annoyance from the point of view of a couple of techniques, but it's nothing that really causes any drastic problems at all. It just means you have to be a little bit more careful at a couple of steps where maybe normally you wouldn't be careful. I'm sure that there are some sort of reweighting tricks that you could use to get around it, or you could just be a little bit more careful at the technical detail stage. This is certainly not a large issue, but I would have thought that that some sort of reweighting to make the weighted integers reasonably equidistributed on short intervals, for example, would be an adequate way of doing things if you wanted to do it like that, yeah.
Any further questions? All right, let's thank James again.